And we are back with etching. Okay, etching two types. We saw in the first part what etching is, what are the desirable quality, features, the metrics, and we stopped with with me telling you that there are two types of etching. One is wet and the other is dry. Let's see a little more on these. The first one is wet etching. Now, the one that we saw in photolithography earlier was you were immersing the wafer in a bath of etchant, right? That is actually wet etching. The one that we saw was wet etching. Okay. How do we do wet etching? For example, let us talk about the bath of etchant that we are talking about could be hydrofluoric acid, and that is used, that is HF. HF is used to etch silicon dioxide, which is over a silicon substrate. There are three main steps involved in wet etching. First of all, the etchant species, that means the chemical solution that is going to do the etching process. That etchant species should move to the surface of the wafer, right? When it moves to the surface of the wafer, the etchant species will react with the exposed film. That is the exposed film that it is supposed to etch away. When it comes in contact with that exposed film, chemical reactions occur, and as a result of chemical reactions, products and byproducts are formed. These products that are formed are soluble. You know what soluble means? It can dissolve in the solution. So the products that are formed will dissolve. But at the same time, there will be some particular contamination on the surface of the exposed film. So you have to remove or move away these byproducts from the surface of the exposed film. In order to do that, you have to agitate the apparatus. When you do agitation, the byproducts that are formed will move away from the surface, allowing more of the etchant species to come in contact with the exposed film, thus continuing the process of etching. You got the idea? So first of all, the etchant species should move to the surface of the wafer. Chemical reactions occur. The byproducts are soluble, therefore it dissolves in the solution, and then you have to move it away from the surface, and for that you do the agitation. 3 steps: movement to the surface, chemical reaction, and movement away from the surface. These have to occur in sequence. Depending on which of these is the slowest, that is called the rate limiting step. Depending on the rate limiting step, the etch rate can be determined. And the challenges involved in this wet etching process is, first of all, you have to agitate the entire solution in order to move the you have to move the etchant to the surface and remove the etched product also. For that you need to agitate it, first thing. The second thing is a very interesting problem called resist scumming. Resist scumming comes out as a problem because of desirable quality of the etchant. When your etchant is extremely selective, we already know that being selective is a good thing, isn't it? So when your etchant is extremely selective, this problem happens. Now, what do I mean by that? Look at this. You see the dark portions, though, that is a photoresist which is protecting the oxide below it. Okay, wherever the photoresist is removed, the oxide was exposed and it is removed and it is etched away by the hydrofluoric acid. But look at this particular portion. The photoresist was supposed to be removed fully, but because of some reason such as inadequate exposure or something like that, because of that, this photoresist was not fully removed. It could not be fully removed. Now, even though it is a very thin layer of photoresist, remember that our etchant is highly selective, and even if it sees a little bit of a photoresist, it goes its way. It does not harm the photoresist, because all our etchant is interested in is the silicon dioxide. So it will not touch the silicon dioxide below this thin layer of photoresist. So because of this photoresist, the silicon dioxide below it remains intact, which is not what we wanted, and this problem is called resist scumming. So now you understand by being selective has caused this problem in a way. Okay. So those are the two challenges. Now in wet etching, let us take an example. Silicon dioxide being etched by hydrofluoric acid. The common etchants will be used in a certain ratio. That means 6 parts of water to 1 part of the hydrofluoric acid, 10 parts of water to 1 part of hydrofluoric, or 20:1. Now the etch rate that we achieve here is approximately 1200 angstrom units per minute. Angstrom is 10⁻⁻10 meter. Now, the problem with this wet etching is that it is completely isotropic. That means it will etch in all directions, which of course we know that that's not what we want, isn't it? We want a directional etching. The overall reaction can be summed up like this: silicon dioxide, which has to be removed, reacting with the etchant species, that is the hydrofluoric acid, producing hydrogen, which is a gas, and SiF6 plus 2H2O, both of which can be part of the solution. The HF will be consumed, and the reaction, as time goes, the reaction rate will be decreasing with time. So you need a method by which this HF can be replenished, and we know that buffering agents can be used for replenishing the HF. So buffering agent used here is ammonium fluoride, NH4F, giving NH3 plus HF and back. So in this way you can maintain a constant amount of HF in the solution. Yeah. Some common etchants that we are using is hydrofluoric acid plus nitric acid, that is HNO3, in water. Now if you want relatively more directional wet etchants, you go for mixtures of potassium KOH, isopropyl alcohol and water, that is for silicon. Okay. For gallium arsenide, you go for Br2CS3OH. The good thing about wet etching is, like we said earlier, is extremely selective. That is, it does not touch the substrate at all. That is very good. The problem is, like we saw earlier, it is isotropic. That is what they mean by lack of anisotropic. And the process control is not so good. You cannot, you cannot exactly control the process exactly as you want it to. And particle contamination will be more. The products that are formed, even if the agitation is done, some amount of particle contamination will be there. Yeah. So that is wet etching for you. The next one is ion beam etching. We will see that in the next video, right? Thank you. Okay. Let's continue with ion beam etching. It's a form of dry etching. In ion beam etching, this is the apparatus for it. And if you understand this apparatus, you much about have learned everything that you need for your ion beam etching topic, right? You see here that there is a cathode here and it is heated. When a cathode is heated, it emits electrons. Okay, and when it emits electrons, there is in this chamber, this is called a discard chamber. This chamber is at a very high very high pressure, and this high pressure chamber, you have something you have a inert gas, and that gas is usually argon. The electrons that are produced from the cathode will hit the argon and ionize the argon. That means argon is split into Ar plus ions, that is positive ions, plus free electrons. You have Ar plus and free electrons. Now you have a charged particle atmosphere here in this chamber. These charged particles, you can see at the top and bottom, this is a cross section. So you have magnetic field, solenoid magnetic field provided by this coil. Now because of the magnetic field, a charged particle in a magnetic field experiences a force. Is that right? So the charged particles Ar plus and electrons here, they will experience a magnetic force that will cause them to be repelled away from this discard chamber into the working chamber that you see on the left here. So as it moves from the discard chamber into the work chamber, you can see that it has to pass through a very what do you say, interleaved sort of screen. What you see here is actually a method by which you can collimate the beam. What do we mean by collimate? That means you want to get a parallel unidirectional beam. So in order to do that, it has to pass through these two screens here. As it passes through these two screens, you can see that the ions and electrons, as it passes through this, it will pass through this only in one direction, all of them. Okay, the slots are arranged in such a way. Now, only if they are moving in the same direction that is parallel to the structure, that is only then it will pass through it and you have a collimated beam. Once the beam is collimated and it enters into the chamber, now it can be neutralized. The argon ions and electrons can be neutralized. How do you neutralize it? By allowing recombination of the argon ions and the electrons. When recombination is happening, it becomes neutralized, and these argon, they continue along this path as they are energized, and they continue along this path and they come and hit the wafer that is placed here. You see that there is a hinged stand here, and on the hinge stand the wafer is placed, and the wafer is placed at an angle such that these incoming argon atoms will come and collide with the surface of the wafer and thus etch away the surface of the wafer. Now you have to notice that this is a strictly mechanical process. There is no chemical reaction or process involved here. It's a strictly mechanical process, right? So this is how etching happens in ion beam etching. These are the details as I have already explained to you. Please go through the PPT. Now, since it is performed with ions and since it is approaching it in only one direction, the very good thing about it is that it is highly anisotropic. That means it is more or less directional. The problem with it is it goes and hits the surface and just about hits anything that in its path almost, and therefore the selectivity is extremely poor. The throughput is one wafer at a time, as you have seen, and the directionality is good. No chemical reactions, strictly mechanical process. Advantages, like we saw, just as we saw right now, is directionality. Directionality is good, and second thing is applicability. Actually, it can pattern just about any material. Okay, so the wide variety of materials that it can erode or etch away is really high. Disadvantages, first of all, selectivity. Like we said earlier, it just about etches anybody in its path. So the photoresist to underlying layers selectivity is 1:1, which is really bad actually. Now throughput is one wafer at a time. Again, we saw that in the figure. The erosion rates is pretty slow, and you need high vacuum for this, right? Next one is plasma etching, the last one. This is also part of dry etching. Plasma, as you might already know, is a state of matter that is similar to gas, but it is electrically neutral in net. But actually it consists of both positive as well as negative particles. Now we are going to do etching in a plasma environment, that is plasma etching. This is plasma etching. This is the setup for plasma etching. You see that this is the plasma environment. The plasma environment, the gas that enters into this environment is caused to split up into ions and electrons. That is your plasma environment. It comes to the surface of the wafer. It is adsorbed by the surface of the wafer. Adsorbed means it forms a thin layer on the surface of the wafer. It is not absorbed into it. It is adsorbed. That means it forms a thin layer on the surface of the wafer. It reacts with the material on the surface or the layer on the surface of the wafer. After reaction happens, some byproducts and products are formed that can be desorbed. That means it moves away from the surface of the wafer and it can be exhausted out. The gas is exhausted out. These are the steps that I just told you right now. The feed gas is introduced into the chamber. It breaks down into chemical reactive species by the plasma, and the species will diffuse to the surface of the wafer. It is adsorbed. They move on the surface until they react. Reaction products are desorbed and diffused away from the wafer and transported out. This is an example that you can go through for plasma, just as we saw for wet etching. The advantages of plasma are it is easier to start and stop, it is less sensitive to wafer changes, it is highly anisotropic, few particles are produced, and less chemical waste. So that's it for plasma etching. Thank you. Study well.